Returning to the normal distribution, and what I have here is the 10 Deutsche Mark from before they had the euro in Germany. And here is a picture of Gauss. Remember I said to you that it's also called the Gaussian distribution. And here in the background, I don't know if you can see it, but there is the normal curve that he's famous for. We'll come back to Gauss when we look at least squares and regression. This Gaussian distribution, we introduced it as a asymptotic development as n becomes large in the binomial. But it stands on its own right too, as you might suspect from the name normal. And in fact, we didn't introduce it then. We introduced it a long time ago when we looked at the histogram for the Framingham heart study. And here are the logarithms of the diastolic blood pressure that you saw earlier. And there it is. That's very approximately normally distributed. Here is the glucose level at visit 1 for the non-diabetics. Remember, the diabetics are down here. Maybe these guys haven't been diagnosed yet as diabetic. Maybe they're pre-diabetic. But other than that, it's pretty much normally distributed. Here's another one. This is the BMI, the body mass index, at exam 1 for people from the Framingham heart study. And it too looks pretty normally distributed. So the normal distribution, my point is the normal distribution stands on its own merits too. And there it is. So there is the mathematical definition of the normal density function. And the one I've plotted here actually centered around 0, because these things are centered around the mean mu. So this is like the mean is 0. And I've also set the sigma squared equals 1. So this we've set equal to 0. This we've set equal to 1. And that is what is called the standard normal distribution. And here's the plot of the standard normal distribution. All normals are symmetric. So if I spin it, if I had drawn a straight line and I spin it around there, you wouldn't notice the difference. So it's symmetric around 0. So there it is. It's symmetric about mu, which was 0 in this case because we set mu equals 0. The spread is determined by sigma. So going back to the previous thing, had I used, so here I've used sigma equals 1. Had I used a bigger sigma, I would get something that looks flatter like this. Had I used a smaller sigma, I would get something that's a little bit tighter like that. It's symmetric about mu. The spread is determined by sigma. And the standard normal is the one I drew for you in the previous slide. And that's the one that has mu equals 0 and sigma equals 1. So if you actually look at tabulated values of the normal distribution, this is the one that gets tabulated. We're not going to do that. We don't do that anymore because we have Stata doing the work for us. So we have computers to do the work for us. Now, what we can do is we can look at this distribution and start asking questions. If this is the real distribution, say of BMI, whatever, what proportion of the people have values in here? Or what proportion of the people have values up there? What proportion of the people have values down here? Describe this distribution for me. And the answer is, it's very much like the Venn diagram. If we have the total area under the curve is equal to 1, and that's why we have this thing out here, that ensures that the integral of this, so the area under this whole curve is equal to 1, then I can answer that question of what proportion is up here by looking at this area. What proportion is up here? I just have to look at this area. Let's look at some particular examples. The one that everybody remembers is that the area to the right of 1.96 is 0.025. So for a standard normal, there's a 2.5% probability of getting a value bigger than 1.96, which is, let's say 1.96 is approximately 2. That's approximately 2. So the area to the right of 2 is about 2.5%, 0.025. Starting to ring a bell already with the empirical rule? Okay, so there it is. The area to the right of 1.96 is 0.025. Other ones that we use are if we look at 0, the area to the right of 0 is 0.5. So it's symmetric. Total area is 1, so the area to the right of 0 has to be 0.5. The area to the right of 1.65 is 0.049. So this one we've just spoken about. When it's approximately 2.5, the area is 0.005. And when it's 3, the area is 0.001. Now, this thing is symmetric. So the areas on the other side flip this whole thing, and we get that the area to the left of minus 1.96, minus 1.96, the area to the left of that is also 0.025. So the area to the left of these numbers are exactly the same as the area to the right when I change the minus signs to plus signs. I can get this from the function normal in stata. If you actually want to be precise, there are the values. But what I get from this too is, so if I know the area in the right tail and I know the area in the left tail, that means, and the total area is equal to 1, I can give you the area in the middle. So for example, the area between minus 1.96 and 1.96 is 0.95, because the area here was 0.025 and the area here was 0.025, and the total area is equal to 1. So the area in the middle must be 0.95. Now this is the standard normal. Remember with the standard normal we said that had a mean equal to 0 and it has standard deviation equals to 1. So here we are at 0, and we go up to 1.96 and down to minus 1.96. In terms of this, what does that translate to? It translates to the mean plus or minus 2 standard deviations. The mean plus 2 standard deviations is 1.96, approximately. The mean minus 2 standard deviations is minus 1.96, approximately. And that covers 95%, exactly 95% of the total area. All right? No more approximation. This is the idealization of the empirical rule. Mean plus or minus 2 standard deviations gives us exactly 95% of the data. And you can get the other plus or minus 1 standard deviation, plus or minus 2 standard deviations. You can figure that out for yourself and see that this gives it to you exactly.